another video lecture in the series on zero stability. This is section 6.4, part 3, and this is just a quick example for you. So let's get started. Here's an example straight out of your textbook. It's example 6.4. It's a linear multi-step method that is in equation 6.29. And note that in the text, we're given that this method is consistent. So let's assume that to begin with. And the job here is to assess zero stability. Now, what does that mean? Well, recall that really means we're applying this method to u prime equals 0 with u of 0 equals 0. So zeros everywhere. What could go wrong? A lot, of course. So let's start by looking at the difference equation that you get from applying zero stability to equation 6.29. So the left side sticks around and the right side gets set equal to 0. The characteristic polynomial that you should be looking at is rho of zeta. And that's a pretty nice one, right? That thing factors. So you have a nice zeta minus 1 quantity squared is equal to 0. So what you have is a repeated root of magnitude 1. I spoke about this a bit earlier in the previous video. So your general solution to this difference equation is, well, it's C1 times 1 to the power of n, because my first root is 1. And then because I have a repeated root equal to 1, I get an n times a 1 to the n. So once we clean it up a little bit, it is C1 plus C2 times n. And our starting values are, of course, UN when n equals 0 is just U0. And then when n equals 1, my UN is U1. So here's my little linear system of equations that I want to solve. And you can see that C1 and C2 will turn out to be this. All right, so this is my expression for all values of n for what my approximation will look like if I'm solving just that trivial initial value problem. So now here's what I want to do. I want to say, all right, I know that the true solution to this trivial IVP is just 0 for all values of n. However, what if I have some error? What if I've got some kind of error? So my solver jumps off of 0, takes a little step up to k. Then what happens? Well, if u1 is equal to k, plug into that arrow looking thing right above it, and this is what you come up for each n, for each iteration in my steps, I get un is equal to k times that value of n. So now let's think about this back in terms of this convergence idea, that I want to think about taking the limit as n goes to infinity, or I guess k goes to 0, of what happens to un. Well, it turns out that then that becomes k times n, right? Because of this expression right here. And when that happens, well, k times n, capital N, is t. So the limit as k goes to 0 is just t. So it turns out that this particular linear multi-step method that I started with way up here at the beginning, if I apply it to the 0 initial value problem, and I have a little bit of error in U1, what I will come up with is that approximation scheme is going to converge to basically u of t equals t instead of u of t equals 0. That's what it's going to look like if you actually hammer out those iterations. That means we've got a linear multi-step method that does not converge to the right thing. So what happened here? We've got a repeated root with modulus 1, right? That's what happens when we have a repeated root with modulus 1. Our linear multi-step method is not going to converge. So this example illustrates that. Notice if you look at example 6.5 in your textbook, you have a nicer case where you've got, a repeated root with modulus less than 1. That case is going to be a little nicer, and you're going to have convergence in that case. So I encourage you to take a look at that on your own. Here is kind of the lead up to the theorem. So if I have one of these characteristic polynomials with a root zeta j that is repeated m times, what happens on that? Un is going to involve terms of the form n to the power of s times zeta j raised to the n, where s goes from 0 to m minus 1. That's just a product of when you have repetition in your difference equation. This is how you write down your linear combination of your general solution terms. In terms of what we're thinking about here, which is what happens to this term, as long as zeta j is less than 1, then there's no problem. All these terms are going to go to 0, just like you want them to. It's only when you get to a repeated root, which has magnitude 1, or of course something larger than 1, where you're going to run into this problem where you don't have convergence. That is the end of this particular case. Thank you for joining me for this video. I'm going to move to the next video where now we're going to actually state a couple of explicit definitions. And all right, thanks for joining.